Hello, this is my lab 6 for physics 2. In this lab, the purpose was to observe the Curly electric field and current that produces a magnetic field that exerts an external magnetic force. We collected observational data of the magnet falling through the conductive aluminum foil tube, and we created a computational model for the magnet and tube interaction. And the findings were the magnetic field creates a force that cannot counteract gravity and allows the magnet to fall at the downwards net force. The experimental time was 0.334 seconds, and the computational time was 1.122 seconds. Key concepts here were the magnetic field of a dipole. This one was really essential. Um, it includes mu naught over 4 pi, and then we have mu, which is just the bar magnet dipole. Force on the loop, that was also important. You take the current, and then 2 pi r is the circumference. And then you have the magnetic field, and then you do some cross products there as well. You also have change in flux with time. This is essential for finding the current because you take the negative change in flux with time and divide it by the resistance um, to get the current. And then we also have force gravity, just basic mg, and then Newton's second law to advance the position and velocity as well. So for this model, we have the bar magnet. The north end was dropped downwards, so that was found prior to the experiment, and the south end was at the top, and so the magnetic dipole goes from the south to the north direction, and then you have force gravity pulling it down and force magnetic, pardon, pulling it up. But we determined that force magnetic cannot counteract gravitational force, so it does fall. The source was the bar magnet, and then the aluminum foil tube was induced. So there is an induced current above and below the bar magnet. Here's the experimental video. You can see the bar drops through the aluminum foil tube. We did 5 trials and then took the average for an average time of 0.344 seconds. Here is the code. At the top, you can see the geometry of the tube, so those were measured. You also see the properties of the magnet. So mu mag, the magnetic dipole moment, was taken from a prior lab. Additionally, this is how we computed the B field. It is an iteration, as you can see. So that was the equation that was stated earlier. And then from there, you can find d flux. That's the 115 to 122 lines of code, using the ring radius and the distance. And then you can find the numerator and denominator using the equation mentioned before. 149 shows the gravitational force. The gravitational force is solely in the y component. And then once you have d flux dt, you can find the current as stated earlier. And then you can find B ring, B hat, sine theta to find the magnitude of the force on the ring and on the magnet. And then that allows you to find the total magnetic force on the magnet. And then to find the net force, you find the magnetic force plus the gravitational force. And then from there, you can update the velocity and position using Newton's second law. Here is the video that was produced. You can see the blue and the red video on the video, and those represent the induced current. You can see the magnet falling down. There's also a nice graph over here. So that kind of shows what's going on throughout this experiment as well. You can see it accelerating downwards and then kind of tapering off with the velocity as it goes more constant, and the total time in the tube was 1.122 seconds, which is different than the computational value. In conclusion, the magnetic field creates a force that cannot counteract gravity and allows the magnet to fall with a downwards net force. The experimental time was 0.334 seconds, computational time was 1.122 seconds. And so the computational model was not as accurate as it could have been and did not correctly display the actual times. Potential sources of error could be human error, measuring distance and time, electronic devices nearby would affect the force, and also friction against the sides of the tube was neglected. If the resistivity of the conductor was reduced as close as possible to zero, how would the dynamics of the falling magnet change? This is plays into Ohm's law, which is I equals EMF over R. So R is in the denominator, so the current would increase if the resistivity decreased and create a greater magnetic force, which would counteract the gravitational force, so the magnet would not fall, it would just stay put. And this is a little bit unrealistic. If holes or slots were cut into the tube, how would this affect the ring currents in your model? Induced currents in the aluminum tube would be disturbed and decreased, so the magnet would fall quicker because there would be less force acting upon it.